I'm sorry, another theorem for you to copy in your notes. This one's also called sometimes the IMT, the invertible matrix theorem. Let's talk about why this might be true. So what we're saying here is that if one of these statements is true, then they are all true. And if one of them is false, then all of them are false for a matrix A. So let's talk about why 1 implies 2. Okay, so if 1 is true, why does that mean 2 is true? Okay, if A is invertible, then why does this homogeneous system only have one solution? Well, if I have the homogeneous system, then I can multiply both sides by A inverse, can't I? And I get x is the 0 vector. Now, how about 2 implies 3? Now, if I assume that 2 is true, how can I prove that 3 is true? 3 is true? Jeepers. Well, you know, if ax equals 0 has only the trivial solution, let's just assume 3 by 3. What does that mean? What must that mean? If it has only a unique solution, the 0 vector, that must mean that this augmented matrix row reduces like so. Okay, there's no other way you're going to have a unique solution. X equals 0 vector. Okay, so if I assume 2, then this augmented matrix must follow this path, meaning that A must be reducible to IN. Okay, how about 3 implies 4? So if it can be carried to the blah blah by the blah blah, well, okay, now I'm going to have my A and my B here in an augmented matrix. And it has at least one solution. Well, I know that when I reduce this, I'm going to get something like this. Okay, I'm assuming that 3 is true. I'm assuming that the matrix A can be reduced to the identity. So that tells me that this augmented matrix must go to this augmented matrix. And I can see here that I have a pivot for every row. So this is consistent. Meaning exactly 4. Okay, this system has at least one solution. That's what consistent means. I have at least one solution. Okay, so from the assumption that A can be reduced to the identity, I get that AX equals B must have at least one solution. And I can see it here. Okay, 4 implies 5. This is a little bit trickier. 4 implies 5. What are we doing here? What are we doing here? Seriously. So it has a solution. So there's a matrix. So what I'm trying to do is I'm trying to show that I can find a matrix C that does this for me. But what I'm trying to do there, well, let's see what I'm trying to do. I got C1. Let's just say 3 by 3 again, just to cut down on extra notation here. So I'm trying to find a C that will make this happen for me. But using my definition of matrix multiplication, I get this. Let's take I, and we'll take I, and we'll write it as 1, 0, 0, 0, 1, 0, 0, 0, 1. So if I'm going to have a C that does this for me, what does that mean? I need to have a solution. I need there to be a solution to AC1 equals 1, 0, 0. And I need there to be a solution to this equation. And I need there to be a solution to, that's a 3, to this equation. And if I'm assuming 4, then these have solutions. At least one solution. And that does it for me, right? Okay, so assuming 4, these 3 equations have solutions, which means I can find C. I can find C, the matrix C, that makes this equation true. The first column is going to be my C1 that I find. The second column is going to be C2. The third column is going to be C3. 5 implies 1. 5 implies 1 is a bit delicate, a bit tricky, so it's something I think you'd better off reading. So please have a look in the textbook if you're curious about that one.